Maths Aspirants Groups organizes online problem solving sessions to help the students who prepare for different competitive examinations. As a part of that series, today we have a session on Jordan canonical forms, which is an advanced topic in linear algebra and is a very important topic for examinations like NET and GATE. So today we have Mr. Renjith T is with us to discuss this topic. Renjith is currently pursuing PhD at Indian Institute of Science, Bangalore. I express my gratitude to Renjith for joining with us. I welcome everyone to this program and hope that today's session will be really helpful in your preparations.
First of all, I thank Dr. Vinod Kumar to give me this opportunity. So, as he said, Jordan canonical forms, for us it is some advanced topic because in my master's degree, it was not in the syllabus. So I'm going to talk about Jordan canonical form from the scratch. Like, I'm not assuming any previous knowledge of Jordan canonical form to solve any problems or anything. But since this is a net solving session, I'm starting from the point of diagonalizability. So I assume that everybody in this group has some knowledge about basic linear algebra of linear operator and up to diagonalizability, the eigenvectors, characteristic polynomial and everything. So I'm starting from the point of the issue where we are lacking diagonalizability. And then I will explain what is Jordan canonical form and we will do some problems. Okay. So my first question is, all or matrices diagonalizable? So since all of you are preparing for this competitive exams, you might come across a lot of matrices which are not diagonalizable. Okay. So when we say matrix is diagonalizable, so we'll say that a matrix is diagonalizable if it is similar to a matrix which has only entries in the diagonal and other parts are zero. Or we will say in other forms like, if you have a basis containing only eigenvectors, you will say that that matrix is diagonalizable. But when we say it is not diagonalizable, you may come across issues like if your characteristic polynomial is x minus 1 whole square, minimal polynomial is also x minus 1 whole square, then you will say that it is not diagonalizable. So all these things you guys might know. So here we are lacking the eigenvectors. Okay, so here you have eigenvalue have 1 have multiplicity 2, but it does not have enough eigenvectors to form a basis. You will find only one eigenvector. Okay, that's what the main you are using while diagonalizability. Okay, so sorry, 2 calls were coming in between, that's why. Okay, so that's not the main issue we are facing while doing diagonalization. So we will start with the basic or the most simple form of the matrix which is not diagonalizable, that you might know it is nilpotent matrices. So what are nilpotent matrices? If A n by n is called nilpotent. Okay, so this is the definition of a nilpotent matrix. So what does mean the nilpotent? It is going to zero if a matrix is nilpotent if a power k equal to 0 for some k. So now you know that its minimal polynomial will be x power k, and you know that the only characteristic values are 0. So if the matrix A is diagonalizable, then the only diagonal values will be 0 and it will become a 0 matrix. So a nilpotent matrix is diagonalizable only if it is 0 matrix. A is diagonalizable only if A is identically equal to 0. So we know that there are a lot of other nilpotent matrices which is not identically equal to 0 but is still nilpotent. So these are the very basic examples of matrices which are not diagonalizable. Okay, so we will start with the nilpotent matrices. So what we mean by Jordan canonical form is we want something very close to diagonal matrix. So diagonal matrix means it will have entries, I mean non-zero entries only in the main diagonal. So we want something which is nearer to that, means as much as less or non-zero values. So okay. So for example, I'm taking a very simple matrix. A is a 2 by 2 matrix such that A square is 0 and A not equal to 0. Okay, so this is a very basic matrix. So we know that it is not diagonalizable. So that is one important point. So this is a usual question in net. Here they will give nilpotent matrix and ask whether it is diagonalizable or not. So even if you just go somewhere with Jordan canonical form, this is a basic knowledge you should acquire. Nilpotent matrices are never diagonalizable unless it is 0. So A is a 2 by 2 matrix such that A square is 0, A not equal to 0. So you know that this is not at all diagonalizable. Okay. So now our question is, what is the best way to write in the simplest form? Okay. So to write a matrix, what we need a basis. Okay. So since A not equal to 0, we will get a U belongs to that vector space V such that AU is non-zero, right? Because if so, 1 minute, my guide is calling. Sorry. Yeah, I'm extremely sorry. My research guide was calling. Vinod Kumar. Okay. So you will get a U belongs to V such that AU not equal to 0. Okay. So now because if you can't find such a U means A is identically equal to 0. Okay. So you will get a U belongs to V such that AU is not equal to 0. Then take these two elements, AU, comma U. So it is easy to prove that this is linearly independent. Okay, so this is, I'm leaving it as an exercise. So prove that this set is linearly independent. So A is a 2 by 2 matrix with A square equal to 0, A not equal to 0. U belongs to, then you will find the U belongs to V such that AU is non-zero. Then you will get a 2 element set which is linearly independent. So since it is linearly independent, it will form a basis. Now compute the matrix of A with respect to this basis. Okay. So what will be the first element? A of AU. It will be A square U and it is equal to 0. So what will be the first column? It is 0. Then what is, sorry, it is 2 by 2 matrix. So first column will be 0. And what is the image of second one? A of U. That is nothing but AU. It is 1 into AU plus 0 into U, right? So what will be the second column? 1, 0. So if A is an nilpotent matrix with A square equal to 0 and A not equal to 0, it has a basis with this form. Okay, then A is similar to this matrix. A is similar to 0, 1, 0, 0. Or you can find a matrix P and P inverse such that A is equal to P 0, 1, 0, 0 P inverse. That means this is nothing but the coordinate matrix. Okay, so this is what we called the Jordan canonical form of the matrix A. So A is not diagonalizable, but it is very close to the diagonal matrix. I mean, in the main diagonal there are zeros. And just one row, there is one. Now just think about the 3 by 3 case. A is a 3 by 3 matrix such that A cube is equal to 0 and A square not equal to 0. So this is also not diagonalizable, because if it is diagonalizable, the only option is it must identically equal to 0. So we get a U such that A square U is non-zero. Since A square U is non-zero, AU also is non-zero, and U is also non-zero. Similar thing, exercise. This is linearly independent. Okay. So now you got a basis for V 3 by 3 matrix. So there will be 3 elements. It is linearly independent, so it forms a basis. Now compute the matrix corresponding to this matrix. So what will be the image of first one? A of A square U, it will be 0. So first column is 0. What is A of AU? It is A square U. So corresponding to this basis, A square U is 1 0 0. I hope everybody got this. It is just because of this basis, 1 into A square U plus 0 into AU plus 0 into U. That is 1 0 0. Then what is A of U? It is AU. So it is 0 into A square U plus 1 into AU plus 0 into U. So 0 1 0. Okay. So this is a Jordan canonical form corresponding to this matrix. So this is a more simpler form. Okay. Similarly, if you just write like A 3 by 3 A cube equal to 0, sorry, A 3 by 3, it can be like this also. A square equal to 0. Here we take A cube equal to 0. One more option, A square equal to 0. So here A square equal to 0 means range of A is contained in null space of A, right? Otherwise you can't get A square equal to 0. If you can't, so this is, if you can get it, it is easy to prove. If range of A must be contained in null space of A, then by rank nullity theorem, null space of A, nullity of A must be bigger or equal to range of A, and the sum must be equal to 3. So the only option is nullity of A must be 2. Okay, so this is an important data we need. Okay, so we have nullity 2. Now you have 3 by 3 matrix, A square equal to 0, and A is non-zero. So you can only guarantee that you will get a U such that AU is non-zero, because only the A matrix A square is 0, A is non-zero. So you will get a U such that AU is non-zero. Okay, but A square U is 0 means AU belongs to kernel of A. Okay, so AU is in the kernel. Now you know that nullity of A is 2, means there is 2 dimension in the kernel. So there are 2 dimensions for the kernel. So you already got one element AU in the kernel. U is not in the kernel. So you will get one more element, some V. Okay, so AU belongs to kernel of A. Since dimension of kernel A is 2, you will get a V also belongs to kernel A. So U and AU are linearly independent. You can prove as before. Also, you will get V is another linearly independent element in the kernel. So AU and V is also linearly independent. So this set forms a basis. Okay. Now, what is the matrix corresponding to this? What will be image of AU? A of AU will be A square U. It is equal to 0. So the image will be 0. A of U is AU. So it will be 1 0 0, and V belongs to kernel, that means 0 0 0. So this is a Jordan canonical form corresponding to this matrix. So for a 3 by 3 nilpotent matrix, we wrote 3 forms: 0 1 0, 0 0 1, 0 0 0. This was one form. Another form: 0 1 0, 0 0 0, 0 0 0. And the single matrix here. So these are the 3 possibilities. So because we covered all the possibilities. So if a 3 by 3 matrix or nilpotent matrix, then these are the only 2 possibilities of Jordan canonical forms. Okay. So this is how we are going through Jordan canonical forms. Now, so if here in this stage, here you know that here the kernel of A is only one dimensional, right? Because U and AU are not in the kernel. A square U is one in the kernel. Okay, so the geometric multiplicity of here, I mean here 0 is only eigenvalue. Geometric multiplicity of 0 is dimension of the kernel. So dimension of the kernel is only 1. Okay. So A square U is the only eigenvector here, and the other two things are called generalized eigenvectors. In this case, AU is in the kernel of A and V is in the kernel of A. Okay. Here AU belongs to kernel A and V belongs to kernel A. So these two things belongs to kernel A. That means they are eigenvectors. Okay. So AU and V are eigenvectors of A and U is generalized eigenvector. Okay. Generalized eigenvector. Okay. So that's what we are doing. In the diagonalization process, we need a basis comprising of fully eigenvectors. Okay, but all the matrices are not diagonalizable, so we can't get a basis with fully eigenvectors. So we will add some more vectors to it, which is called generalized eigenvectors. Okay, so I'll just give one example with non-nilpotent matrix. Okay, so consider a matrix A. Consider A 3 by 3 with, so here for simplicity I am taking only characteristic values with same characteristic values. A 3 by 3 with characteristic polynomial x minus 3 whole cube. Okay, so here you know that there are 3 characteristic values, but all the 3 are 3. So the algebraic multiplicity of 3 is 3. Now if kernel of A minus 3i has dimension 3, then we are done. If kernel of A minus 3i has dimension 3, then you will get 3 elements u, v, w. Okay, these 3 elements in the kernel of A minus 3i. Then what will be the image? A of u will be 3u, A of v will be 3v, A of w will be 3w, and the corresponding matrix will be 3, 3, 3. The diagonal matrix 3, 3, 3. So if you have enough eigenvectors, if kernel of A minus 3i have enough eigenvectors, then we are done. Okay. Suppose not. If kernel of A minus 3i has dimension 2. Okay. So you have only dimension 2. Then what will you do? Then you know that what will be the eigenvalues of A minus 3i? Since eigenvalues of A is 3, all eigenvalues of A minus 3i will be 0. Right? Since all eigenvalues of A is 3, so eigenvalues of A minus 3i will be 0. That means A minus 3i is a nilpotent matrix. And what about dimension of its kernel? It is 2. Then you will get that A minus 3i whole square will be 0. Okay. Here, such that A minus 3i is not equal to 0. So here, the kernel has only dimension 2. That means you don't have enough eigenvectors here to form a basis to get diagonalizability. If you have enough eigenvectors to form a basis, then you will get diagonalizability. So here, the kernel of A minus 3i has only dimension 2. So you can't get enough eigenvectors to form a basis. Okay. So here, you have only dimension 2. Since A minus 3i is not equal to 0, you will get an element u such that A minus 3i u is non-zero. Okay. If it is 0, then A minus 3i u will be 0. Since it is non-zero, we will get at least one u such that A minus 3i u is non-zero. If you apply it again, then you will get it will be 0. Now, comprise of u, and since it has kernel of A minus 3i as dimension 2, this is already in that kernel, you will get one more element v. Okay. V belongs to kernel of A minus 3i. So what are the elements in the kernel now? This A minus 3i times u is there and v is there. So there are 2 elements already and one more vector u. This is what we call generalized eigenvector. Then what will be the basis? I mean matrix corresponding to this basis? What? if you give a of a minus 3i times u, okay, just simple computation, this you can add and subtract 3i here, then it will be a minus 3i of a minus 3iu plus 3 times a minus 3iu. So this part will be 0 because a minus 3i whole square is equal to 0. So a minus 3i times a minus 3i times of u will be 0, and this is nothing but 3 times a minus 3i of u. Okay, so in the first column it will be 3 times of first element, 0 times second element, 0 times second element. So the first column will be 3 0 0. And what is image of second one? Okay, I am calculating here. What will be the second one? AU. Okay. So AU will be, you can write like a minus 3i times u plus 3u, right? So here 1 times the first element plus 3 times the second element. So it will be 130. And what will be AV? I already told that V is from the kernel of a minus 3i. Okay, V is from the kernel of a minus 3i. That means a minus 3i times V is equal to 0, which means AV is equal to 3V. So it is 0 times first element plus 0 times second element plus 3 times the element. Its image will be 0 0 3. So this is a Jordan canonical form of that matrix. So these are all the things I just gave for a motivation that how the Jordan canonical form is coming. So if you just take a matrix and try to find out its eigenvalues and eigenvectors, if you don't have enough eigenvectors to form a basis, you will just generate some generalized eigenvector also. So in this case, the eigenvectors are a minus 3i times u and v. Since eigenspace has only dimension 2, there will be 2 elements in the eigenspace. And to make it Jordan canonical form, we are introducing one more element, which is called generalized eigenvector. So this is a process of doing Jordan canonical form. Okay, now I'm just stating the theorem. Now I'm just done with these examples, and we will move to the other kind of problems. Okay.
Hello, Renjith. Some issue, Renjith. Dear participants, please wait. Some technical issues on the side of Renjith. Let's wait.
Okay, sir.
Yeah, Renjith. Renjith, you are muted. You are muted, Renjith.
Hello, sir. Now.
Yeah, now it's okay. If any problem with video, you can switch off the video. No problem. Okay.
No. Issue was not with video. One Flipkart guy was keep on calling. So if I didn't attend, then it will come again and again that calls. That way I just attended.
Okay.
Sorry.
Okay. No problem. Just continue.
Yeah. Okay. So here this is a Jordan canonical form for the matrix. Okay, so now I'm just stating the result. So if you have any matrix, so this is, here I'm doing it only the case with single eigenvalue. So what Jordan decomposition theorem says is that even if you have different eigenvalues, you just consider it as a different sections. Okay, so it is like if you have a characteristic polynomial A with x minus 3 whole cube and x minus 1 whole square. So here you consider the matrix two different matrices, one with the section only eigenvalue 3 and one with the section only eigenvalue 1. Then you can write the matrix in different blocks. Okay, so you will get a basis such a way that in one block you can deal with only eigenvalue 3 and another block you can deal with only eigenvalue 1. Okay, so in eigenvalue 3, what will be, as we said, if you have the kernel of a minus 3i, we will look. If you have a kernel of a minus 3i has dimension 3, then in that part it will be diagonalizable. You will have enough eigenvectors corresponding to 3, and you will consider kernel of a minus identity. If you have enough eigenvalues for eigenvectors for kernel of a minus I, that is, it has dimension 2, then that part it will be diagonalizable. Okay, so if you have like that, then it is done. If kernel of a minus 3i has only dimension 1, okay, if kernel of a minus 3 has only dimension 1, then what will you do? Then you will have only one eigenvector. Okay, then you will have only one eigenvector. And other things won't be eigenvectors. Okay, and if this has only dimension 1, then there will be only one eigenvector. Okay, so in such cases, what will we do? Okay, so in such cases, you can deal the things separately. Okay, so here there is only one eigenvalue, and here is the minimal polynomial is itself x minus 3 whole cube into x minus 1 whole square. That means you have the a minus 3i whole cube will be 0 in the top part. Okay, then now we are dealing the matrices in two different parts, in the upper part and lower part. So in the upper part, a minus 3i whole cube will be 0, and a minus 3i whole square is not equal to 0. Okay, so here, since a minus 3i whole square is non-zero, you will get the u that a minus 3i whole square u is non-zero, a minus 3i u is non-zero, and u is. So you will have three elements there. Okay, so here if you apply a minus 3i in the first element, you will get 0. So this will be an eigenvector corresponding to your matrix, and the other two are generalized eigenvectors corresponding to that. Okay, and here a minus I is non-zero, but a minus I whole square is 0. That means you will get a v and a minus I times b. Okay, so there will be a lot of gaps in this because we are not doing the whole theory in process. I'm just going through a rough idea. So what are the things we are doing? Okay, so here if you write the matrix, sorry, it will be a 5 by 5 matrix. If you apply the first one by simple calculation, you will get it matrix like this: 3 0 0 1 3 0 0 1 3. This will be the first part, and the second part, it will be 2 by 2 matrix with these two are the generalized eigenvector. The first one is an eigenvector and second one is a generalized eigenvector. So first vector, it will be 1 0, next one is 1 1. Okay, so this will be the Jordan canonical form corresponding to this. Okay, so this is a Jordan canonical form says if you have a matrix over complex vector space. The complex vector space we mean because we need to find all the eigenvalues. If you have a complex vector space, then you will get all the eigenvalues, and you can find a Jordan basis such that the matrix is the Jordan canonical form. So that is what the Jordan decomposition theorem says. So you can make it in the different blocks. Okay. So I will just say Jordan block. A Jordan block means a k by k matrix with a single eigenvalue k times here and 1 in the super diagonal. Okay. In the just diagonal above, it must be 1. Okay. So here there are two Jordan blocks. In this case, this one is one Jordan block and this is another Jordan block. So in this case, there are two Jordan blocks. So these terms are very important because in the net questions, they are asking what is the number of Jordan blocks, like that. Okay. So in this question, there are three Jordan blocks. If it is diagonalizable, there are three Jordan blocks. Here there are two Jordan. Here there is one Jordan block, and here there are two Jordan blocks. Okay, eigenvalues in the diagonal, one on the super diagonal. So one such part is called a Jordan block. Okay, and here in this case, one part with a single eigenvalue, that is called a Jordan segment. So the matrix with corresponding to a single eigenvalue, that is called Jordan segment, and Jordan block is this kind of one. Okay, so don't confuse with the definitions because I'll tell you one more example. 31303. Okay, so if you are writing this matrix, in this matrix there are two Jordan segments. Two Jordan segments, one segment corresponding to eigenvalue 3 and one matrix corresponding to eigenvalue 2. So there are those two Jordan segments, and this is a Jordan block, and this is a Jordan block, this is a Jordan block, and this is a Jordan block, and four Jordan blocks. So two Jordan. So there are two Jordan segments and four Jordan blocks. Okay. So these are the basic outlines of Jordan decomposition theorem. So when if you got whatever kind of matrix, you can write that matrix in this form. Okay, so you will get a basis such that you can write your matrix in a Jordan canonical form. Jordan canonical form is like you can decompose your matrix like some Jordan blocks. So if I write, I'm just giving some notations. If I write J4 of some lambda, this means a 4 by 4 matrix with lambda in the diagonal and 1 in the super diagonal. Okay, this is what we called J4 of, this is a Jordan block. Okay, if I say J3 of 2, this means 2 0. Sorry. Two 1 0 0 2 1 0 0 0. So this is a Jordan block. Okay, so if I write like J4 of 2, J3 of 2 means there will be a 4 by 4 block with eigenvalues 2 and a 3 by 3 block with eigenvalue 2. Okay, so this will be a 7 by 7 matrix. Okay, so this is what Jordan decomposition theorem says. If you give any matrix in complex vector space, you can decompose it to a Jordan form. That means you will get enough generalized eigenvectors. If you have eigenvectors, then it is diagonalizable. If you can't get enough eigenvectors, you can make it generalized eigenvectors. You can find generalized eigenvectors and make it into a Jordan decomposition form. Okay. So we will do some problems on this. Then you will get more familiar. Okay. So I just want to introduce terms generalized eigenvector, Jordan decomposition form, and Jordan blocks. Okay, we will go through some problems, then you will get more idea about this.
Sir, J32.
Yeah.
Third column says
Sorry,
last
so,
element
yeah.
is.
Yeah, sorry.
Okay.
Yeah, it is 2. Sorry for that. Okay. So we will try to okay. So you have a matrix A 9 by 9 with the following form. Following the Jordan canonical form. I am writing J34, J24, J23, J12, J12. Okay, so I hope everybody now got what is the notation means. This means J34 means there will be 3 by 3 block with eigenvalue 4. That means 4, 1, 4, 1, 4, right? So this is, I mean, the rest of the part is 0. Okay, right? Now a 2 by 2 block with eigenvalue 4. So again 0, 4, 1, 4. Okay, rest of the things are 0. Now a 2 by 2 block of eigenvalue 3. So it will be 3, 1, 3. Then 1 by 1 block of eigenvalue 2 means 0, 2, 0, 2. I mean, rest of the matrix, everything is 0. So now my question is, what are the things you can say from here? Okay. So now you just remember from our definition of generalized eigenvectors, from where did we get one single block? If you are getting one generalized eigenvector, then you are going and you are getting one eigenvector. From generalized eigenvector to eigenvector, we are getting one single block. Okay. So in this block, this is one Jordan block. Okay. So here, this one is coming from an eigenvector. This 4, 0, 0. If A of something is something 4 times that, means it will be an eigenvector. The other two things will be generalized eigenvectors. So these two columns will be images of generalized eigenvectors. Now come about the second column. Here also you will have one eigenvector. 4, 0, it is image of one eigenvector, and this 1, 4 is image of a generalized eigenvector. Okay, what about this 3, 1? Here, this 3, 0 is image of one eigenvector, 1, 3 is image of a generalized eigenvector. This is one eigenvector, this is image of also one eigenvector. So how many eigenvectors you have in total? Eigenvectors corresponding to 4, there are 2 eigenvectors. Corresponding to 3, there is only one eigenvector. The eigenvector corresponding to 2, there are 2 eigenvectors. Okay, so eigenvalue 4 you are considered. What is this algebraic multiplicity? 5. It will be 4 times how? Sorry, it is 5 is the algebraic multiplicity. What will be geometric multiplicity? Geometric multiplicity is the number of eigenvectors corresponding to that. You can easily say. So here, this is one eigenvector. I mean, this is image of an eigenvector. This 4, 0, 0, it is coming. And here 4, 0 is coming. So there are only 2 eigenvectors corresponding to 5. Okay. So, sorry, corresponding to 4. So the geometric multiplicity of eigenvalue 4 is 2. Then next eigenvalue is 3. What is algebraic multiplicity? Somebody can say? Algebraic, how many times 3 is coming? 3 is coming only 2 times, its algebraic multiplicity is 2. What is geometric multiplicity?
1.
Yeah. Geometric multiplicity means number of eigenvectors. So here, A of that eigenvector must be 3 times that. So it is coming only one time, right? A of something is 3 times that. So it is only one eigenvector. The other one is image of generalized eigenvector. So geometric multiplicity is 1. Then what about 2? Algebraic multiplicity?
2.
Geometric multiplicity?
That also 2.
What?
2.
2. Because 2 times eigenvectors are coming. Okay. So these are the things you can get from Jordan canonical form.
Sir, please
Okay.
repeat the geometric multiplicity.
Yeah. So here, what is geometric multiplicity means? The number of eigenvectors, number of linearly independent eigenvectors. That is what we call geometric multiplicity. If you have lambda is an eigenvalue, if kernel of a minus lambda I, if what is the dimension of this one? That is what we called about geometric multiplicity. Yeah, there is much more simpler way. I will tell you after this. Okay. So what will be kernel of a minus lambda I? That is the question. So if we are going with eigenvalue 4, you think about a minus 4i. What will be kernel of a minus 4i? If we remove 4, if we subtract 4, how many columns will get 0? If you remove 4, this column will go to 0. This column and this column are not going to 0, right? So only the first column is going to 0, and this column is also going to 0 if we subtract 4. But this column is not going to 0. So how many columns are going to 0? So that is the number of eigenvectors, right? So that is the number of elements in the kernel. A number of linearly independent elements in the kernel. So what are the number of linearly independent elements? Here one is there, here one is there. So the geometric multiplicity is 2. So there is one more better way. Just count the number of blocks. How many Jordan blocks are there corresponding to 4? Because in one Jordan block there will be only one eigenvector. Okay, each Jordan block is corresponding to only one eigenvector. Rest of the things will be generalized eigenvector. So this 1, 4, and these two columns are images of generalized eigenvector, and this one is the image of the eigenvector. So here also there is one eigenvector and one generalized eigenvector. So there are two parts. One is in this block and this block there will be exactly one eigenvector. Okay, so here the basis part for this will be like a minus 4i times square u, a minus 4i u, and u, right? This will be the basis for first part, and a minus vi times u, sorry, a minus a minus 4i. A minus 4i times 4i times v, a minus, sorry, one more, and v. This will be the basis for the first part, the basis corresponding to eigenvector 4. So there will be, this is be an eigenvector, and these two things will be generalized eigenvector. And this will be an eigenvector, and this will be generalized eigenvector. So what number of eigenvectors will give the geometric multiplicity? So here, if you have the Jordan canonical form, to find out the geometric multiplicity, just count the number of Jordan blocks, because each Jordan block will have only one eigenvector, because other things will be the columns corresponding to generalized eigenvector. So in this Jordan block, there is only one eigenvector. In this Jordan block, one eigenvector. Here there will be an eigenvector corresponding to 3. Again, two Jordan blocks. Understood? Somebody asked me, right? In between. Now you got about the geometric multiplicity. So if you have the Jordan canonical form, then corresponding to each eigenvalue, just count the number of blocks. Then you will get the geometric multiplicity. Geometric multiplicity means number of eigenvectors corresponding to, I mean number of means number of linearly independent. Okay. Now one question. A is a 6x6 matrix with characteristic polynomial x minus lambda whole raised to 5 into x minus mu whole cube, and minimal polynomial x minus lambda whole cube into x minus mu whole square. Okay, so this is the case we are doing. So here you have lambda you are getting 5 times, and mu you are getting 3 times. Okay, so now we separately think about the Jordan segments. Okay, Jordan segments of lambda and mu. Okay, so I am just worried now only about Jordan segment of lambda. Okay, so I am only going to think about A minus,
cross 8 matrix.
yeah, 8 cross 8 matrix, because it is lambda will be 5 times, mu will be 3 times. So to get the Jordan block, I am worried only about 2 segments. Okay, so A minus lambda I am looking about. Okay, so think about A minus lambda I. So we know that A minus lambda I, lambda is coming 5 times. So if we have 5 independent vectors, means if A minus lambda I, kernel of A minus lambda I is full space 5 dimensional, then in that part you have 5 independent vectors, and at that part it will be diagonalizable. Okay, now what the minimal polynomial means, if kernel of A minus lambda I is 0, that means A minus lambda I is 0, right? If kernel of lambda I has 5 dimension 5, then in that part A minus lambda I is 0. Okay, then the minimal polynomial will be x minus lambda, because if A minus lambda I is 0 means, then the minimal polynomial it will be x minus lambda. But what the minimal polynomial is given, x minus lambda I cube. That means kernel of lambda I does not have the whole dimension. You will get only whole dimension if you have A minus lambda I cube. That is the information you are getting from minimal polynomial. Okay, so that is very important. Here minimal polynomial you are giving means, if A minus lambda I has dimension 5, means you have enough vectors to form diagonal basis there. Okay, so the diagonal matrix there. But your A minus lambda I does not give you enough eigenvectors. That's what the information giving from the minimal polynomial, because if you have enough eigenvectors there, then A minus lambda I will be 0 in that portion. But it is not 0. That's what minimal polynomial giving. Minimal polynomial is saying that only x minus lambda cube will give you the 0 part. Okay, so A minus lambda I cube is equal to 0, but A minus lambda I is not 0. Okay, so here I am 0 means, in that part of that I am dividing the whole matrix into 2 parts. So in the part where lambda is coming, that's what I am saying all these things in that part. Okay, so here A minus lambda I cube is 0. Okay, so here now you have one thing. If A minus lambda I cube is 0 means, you will get a u such that A minus lambda I square u is non-zero. Okay, so A minus lambda I square u must be non-zero. That means A minus lambda I u will be non-zero and u will be non-zero. Right, so you will have 3 elements already in the basis which is linearly independent. Okay, so in that part you will get the matrix like this: lambda 1, lambda 1, lambda. So in that matrix there will be a 3 by 3 column. Okay, so that's what in the minimal polynomial. Obviously there should be 5, 2 more things will be there, that is dependent. So if the minimal polynomial has power 3, that means there will be an element such that A minus lambda I square u is non-zero. So there must be a Jordan block of length 3 by 3, of order 3 by 3. Okay, now you need 2 more lambda. That thing can be in other 2 ways. It can be lambda 1 lambda. We don't know which form it is. It can be of this form, or lambda 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 1 1 and lambda 0 lambda. It can be of this 2 form. We don't know which form it will come, but obviously this form will come. Okay, so this is the data it is giving from minimal polynomial. And what about the other part? It was x minus mu whole cube is there, and minimal polynomial is x minus mu whole square. That means A minus lambda I is not lambda. A minus mu I is not 0. Okay, if A minus mu I is not 0 means you will get a u such that A minus ui square is 0. A minus ui times u is non-zero and u. So in effect you will get a matrix like this in the beginning. Okay, because characteristic polynomial has 3 times u, but the minimal polynomial has only 2 times, means A minus ui is non-zero, but only its square is 0. So that means you will get a u such that a minus ui times u is non-zero at that part. Okay. So in that matrix, there will be mu1 mu. This must be there. Okay, in the Jordan block. Then one more Jordan block, it will be coming like mu. Okay. So how can I denote these things? This will be J3 of lambda, J2 of lambda. This will be J3 of lambda, J1 of lambda, J1 of lambda. Okay. And this is J2 of mu, J1 of mu. So in together the matrix will be, there will be two Jordan canonical forms, J3 of lambda, J2 of lambda, then mu, J2 of mu, J1 of mu, and J3 of lambda, J1 of mu, sorry, J1 of lambda. Of lambda, J2 of mu. Okay, so if you have, this is the characteristic polynomial, that is x minus lambda whole raised to 5 into x minus mu whole cube with minimal polynomial x minus lambda whole cube into x minus mu whole square. If you have characteristic polynomial, minimal polynomial like this, then you have two options for the Jordan canonical form, this one and this one. Okay, so these are the important parts. What?
Sir, initially given matrix is 6 cross 6. Sir. Is it possible x minus lambda whole power 5? Characteristic polynomial, sir?
Sorry.
Okay, sir.
It was 8 by 8. Now it is fine, right? I mean, while writing the question, I just wrote start with 6 by 6 and then change the exponents. That's what it happened. Yeah, I hope there is no confusion in this, right? Fine?
No, sir.
Okay. Now there is this observation. Suppose you have, I'm saying a characteristic polynomial x minus lambda 1 power alpha 1, x minus lambda 2 power alpha 2, x minus lambda 3 power alpha 3, like this, and minimal polynomial x minus lambda 1 power beta 1, x minus lambda 2 power beta 2, etc. like this. So now, while writing the Jordan canonical form, what will we do? We will just decompose the sections, right, for lambda 1. So for lambda 1, if a minus lambda 1 I itself is 0, then that part will be diagonalizable. I mean, is 0 in that part, then it will be diagonalizable. But minimal polynomial says that power a minus lambda 1 I power beta will only give you 0 there. Means there will be one element such that till beta minus 1 it won't be 0. So there will be one Jordan block of order at least beta 1. So there will be at least one Jordan block of this order. Okay, so this is one important part you should remember while writing Jordan canonical form. So if you give characteristic polynomial and minimal polynomial, so there will be at least one Jordan block with the power of the minimal polynomial terms. Okay.
Sir, can you say any shortcut from characteristic polynomial to minimal polynomial?
Means? I didn't get the question.
Sir, any shortcut from characteristic polynomial we know. How to find the minimal polynomial, sir? In large matrix.
You can't find. If a matrix is given, then you can find it out. Maybe even if it is a large matrix, it's very difficult. Because for one characteristic polynomial, there will be a lot of different kinds of minimal polynomials, right? If you are saying characteristic polynomial is x minus 1 whole square into x minus 2 whole square, then minimal polynomials can be anything, right?
Yes, sir. Any way to find the minimal polynomial, sir? Minimal polynomial, sir.
From what? That is the question.
Sir, given matrix,
So,
sir.
for a given matrix, yeah, for a given
Yes, sir.
matrix, you have to do, I mean, if it is very big polynomial, it will be difficult. So first try to find out the Jordan canonical form. Then from the Jordan canonical form, you can directly write the minimal polynomial. It is a very difficult part to write the minimal polynomial actually. If it is a general matrix, it will be very difficult to write a minimal polynomial. Because you have to know when it will become zero, right? So if you have given a matrix,
Yes, sir. Yes.
if you are given a matrix A and you are getting eigenvalues 1 and 2, okay, then you will find A minus, if you are finding A minus I, and this is a characteristic, so suppose this is a characteristic polynomial you are getting for A, x minus 1 whole square into x minus 2, okay, and then the eigenvalues are 1 and 2. So to find the minimal polynomial, you should check what is A minus I. If A minus I has null space one dimensional, then its dimension, you have to compute this. Compute A minus I and find the null space of that. If its null space has 2 dimension, then it is diagonalizable in that part and the minimal polynomial will be x minus 1 in that part. If its eigenvalues has in 1 dimension, the eigenspace has only 1 dimension, the minimal polynomial will be x minus 1 whole square in that part. Similarly, another eigenvalue is 2. Then find A minus 2i. If its eigenspace has 2 dimension, then it is diagonalizable in that part, and in that part the minimal polynomial will be x minus 2. If its dimension is only 1, that means it is not diagonalizable and its minimal polynomial will be x minus 2 whole square. You understood what I'm saying?
Yes, sir.
So this much process you have to do if you want to find the minimal polynomial. It is not easy to compute. Because even if you have an nilpotent matrix, A 4 by 4, okay, if it is a nilpotent matrix, then its characteristic polynomial will be x power 4 is equal to 0. To get the minimal polynomial, you have to compute A square, A cube. If A square equal to 0, minimal polynomial will be x square equal to 0. If this is non-zero and A cube equal to 0, then minimal polynomial will be x cube equal to 0. You have to compute and find out. Okay?
Okay, sir.
Yeah. Now, I will do somewhat difficult questions from Jordan block. This is the question. A is a 6 by 6 matrix such that rank of A, R means rank of A is equal to 3, rank of A square is equal to 1, rank of A cube is equal to 0. Can you find out the Jordan canonical form? So it is a 6 by 6 matrix, okay? 6 by 6 matrix means here rank of A is 3, rank of A square is 1, rank of A cube equal to 0. Rank of A cube equal to 0 means A cube is 0 matrix. That means it is a nilpotent matrix of index 3, okay? So what are things you can get from here directly? Rank of A cube equal to 0 and rank of A square equal to 1. So suddenly what you can say? What will be its characteristic polynomial? X raised to 6. What will be the minimal polynomial? X cube, because range of A cube equal to 0. That is A square is non-zero and A cube equal to 0. So the minimum polynomial will be
X cube.
X cube. So there will be one element U such that A square U comma AU comma U. This will be linearly independent and it will form a basis. This will form an eigenvector and 2 eigenvalues. Sorry, generalized eigenvector. So there will be one Jordan block of order 3. That is for sure, right?
Yes, sir.
So there will be one Jordan block of order 3 with eigenvalue 0. I am writing Jordan block of order 3 with eigenvalue 0. Okay. Now, what next? So this is Jordan block of order 3 of 0 will be there. Then we need 3 more points, right? This is a 3 by 3 matrix. Now we need 3 more points. So that 3 more points can be, it can be another J3 of 0. Is it possible?
0, 0, 0, sir.
Huh? So this will be like J3 of 0 means 0, 1, 0, 0, 0, 1, 0, 0, 0. This is one Jordan block. So now a 3 by 3 is missing now. So that 3 by 3 can be one more. So now there are three options.
Single
This can
block, this is 0, sir.
Okay, you are saying this, right?
Yes, sir.
Why not this? Why this is not possible? This is also an option, right?
It is also possible, sir.
Nullity of A equal to 3. Nullity equal to 3. So there should be 3 linearly independent eigenvectors.
Nullity is, here rank of A is 3. Okay, rank of A is 3 means nullity of A must be 3. Okay, by rank nullity theorem. So nullity of A is 3 means there will be 3 linearly independent eigenvectors, or there should be 3 Jordan blocks. Okay, that is most important. There will be 3 Jordan blocks. Okay, so there should be 3 blocks. So how we can split? Now already J3 of 0 should be there. Now the options are, now there should be 2 more blocks. So we have to split 3 by 3 matrix into 2. The only possibility is this one, A2 and A1. Got it? So it must be J3 of 0, J2 of 0, J1 of 0. Okay, if you write it 3, 3, 3, then the nullity will be 4. So somebody told this way, right? So if this is the way, then there are 3 more blocks here, and all these things are eigenvectors. Okay, this one is an eigenvector, this one is an eigenvector, this one is an eigenvector, this one is an eigenvector. There will be 4 eigenvectors. 4 eigenvectors means nullity will be 4. Nullity is 4 means rank must be 2. But here we have given that rank is 3. Okay, so there must be 3 blocks, Jordan blocks. So there are only 3 Jordan blocks. So the answer is, so this is not possible. Now, what about J30, J30? What is the issue with that? If it is J30, it will be like this. Here the nullity is only 2. That is also not possible because we need nullity 3. Okay, so the only possibility is this one. Only possibility is this one. So this is a Jordan canonical form with this matrix. Okay, so you should be careful about all the things given. Another one. Question. A 10 by 10 such that A power 4 equal to 0, A cube not equal to 0, rank of A is equal to 6. So now what are the possible forms? Here it is 10 by 10 and A4 equal to 0 means, and A cube not equal to 0 means there will be one Jordan block with J4 of 0. It is okay, right? Huh? Yeah, somebody was telling something? Huh? Uttam.
Yes, it is okay. This is one 4 by 4 matrix with 0 eigenvalue.
Okay, yeah, once will be there. Now what are the things left? Now rank of A equal to 6 means nullity will be 4. Okay, so there should be 4 other parts. Okay, nullity will be 4. So there will be 4 Jordan blocks. One Jordan block of order 4 and 4 Jordan blocks must be there. Okay, so this is the only information we have. Okay, so with this we have to figure out all the possible things. Okay, so one can have J4, then the sum must be 10. So J4, J4, J1, J1, J4, J3, J2, J1, J4, J2, J2, J2. Okay, so these are the only possibilities. So now my question is, so this was some question in some mid question paper, which are the possibilities. Okay, so there was one more option there. I am not writing that option. So which are the 4 possibilities of this matrix? That was the question. I don't remember which year it was asked. So now I'm adding one more point to this question. So when we can fix this? So here we have different options. So my question is, when we can fix the Jordan form? Suppose they have given rank of A square. Okay. Suppose they have given rank of A square also. So this is Jordan forms of A. Okay. Now I am assuming that suppose they are giving rank of A square. What will be the rank of A square here? So you just think about this matrix. What is J4? 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0. Okay, just take this information. If this is A, then A square will be like this. 0, 0, 1, 0, 0, 0, 0, 1. Okay, you just compute this
2.
and yeah, its rank will be 2. Okay, so if A square, you just think about if 1 is there in this diagonal, then in the square, the elements will be in the one diagonal up. Okay, you just multiply this and verify yourself. If A is this matrix, then A square will have one in the one diagonal up. That will be rank will be 1 less. And what will be A cube? 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. This will be A cube and A raised to 4 will be 0. So this is how it works. Okay. So here if you are trying A square, J4 part will have only J4 have rank 3. Okay. If we are squaring, its rank will be 2. Plus this J4 will also give 2, and J1 will, if you square it, will go to 0. Its rank will be 4. What will be rank here? Square of J4 will give rank 2. Square of J3 will give rank 1, and it will be 3. Here it will be 2 plus 0, it is equal to 2. So if they are giving rank of A square also in the question, because here in the question they are giving rank of A and A raised to 4 is 0. So from that we have 3 options. Okay, suppose they are giving rank of A square also, suppose they are giving rank of A square is equal to 3, then you can fix, which is the Jordan canonical form. Okay. Now, one more question. Problem. A 11 by 11 such that A power 5 equal to 0 and A power 4 not equal to 0. Find bounds on rank and nullity. Yeah, so you have 11 by 11 matrix with A raised to 5 equal to 0 and A raised to 4 is non-zero. So what will be its minimal polynomial? It is X raised to 5 equal to 0. So our question is, what will be the minimum and maximum nullity of this matrix? What will be the minimum rank and maximum rank of this matrix? So if you know about nullity, rank will come automatically. Okay. Can you say, anybody? Here the minimum, what is the minimum polynomial?
Rank less than or equal to 5, sir.
Less than or equal to 5. How?
Less than 5.
Huh?
Less than 5.
Less than 5. How?
Rank can be 8, right?
Rank can be 8. That is important part. Because, see, what will be the minimal polynomial? Minimal polynomial is X raised to 5. Okay. So, one matrix can have 5 by 5, Jordan block 5. So, there will be J5 of 0. So, that is the only restriction we have. One matrix must have Jordan block 5. Right? That is the only data given to us. We don't have any other data. So the matrix can have J5 of 0, J5 of 0, and J1 of 0. Now it becomes 11, right? So this is one option. Then how many Jordan blocks are there? 3 Jordan blocks. 3 Jordan blocks are there. Okay. That means nullity is 3. That is the minimum possible nullity. Okay, so rank will be 8. Okay, so the minimum possible nullity is 3 and maximum possible rank is 8. Okay, now think the other extreme. The only thing is you must have one Jordan block of order 5. Jordan block of order 5. The rest of the things can be anything which should not exceed 5. That's the only thing, right? Now all other thing can be J1 of 0, J1 of 0, etc. I mean, how many times? 6 times. Then how many blocks are there? 7 blocks are there. So nullity is 7. Rank is. Okay. So what is the result we are getting? 3 less than or equal to nullity of A less than or equal to 7. 4 less than or equal to rank A less than or equal to 8. Okay. So this is also some CSIR question. I don't know which year it is asked. So here you are getting the minimal polynomial. From the minimal polynomial, you should get what will be the Jordan block. Minimal Jordan block. From the Jordan block, you will get the rest of the things. Okay, so if you understood these things, then the net exam questions will be very easy. It's not like basic real analysis. In basic real analysis, you are not sure that you will get something. Okay, but if in Jordan canonical form, if you are familiar with some of these topics, then you can sure crack it. This part. Okay. Now, I have one question. December 2014. T 4/4 nilpotent. Okay, it is given T 4/4 is nilpotent, and Ki is equal to nullity of P power I. Then which of the following? Which of the following can happen? So this was the question. I mean, some sentences are different, but this is the main question. T 4/4 nilpotent matrix. Ki is nullity of P power I. Then which of the following can happen? So the options were A, 3 less than or equal to 4 less than or equal to 4 less than or equal to 4. B, 1 less than or equal to 3 less than or equal to 4 less than or equal to 4. C, 2 less than or equal to 4 less than or equal to 4 less than or equal to 4. D, 2 less than or equal to. Yeah, any idea?
Sir, T equal to
Sir, A and D
4 by
possible.
4 0 0 0 1 0 0 0 0 0 0 4 cross 4 matrix.
Yeah, who was talking now? I mean,
Yes, sir.
yeah, what was the thing? Yeah, Subra.
If I take T equal to 0 0 0 1 0 0 0 0 4 by 4 cross matrix.
Yeah, its A square will be 0.
Then
Its
T
square will be 0.
T square equal to 0, T cube equal to 0, T4 equal to 0 matrix.
Yeah. Fine. So
then K1 equal to dimension of car T equal to 3.
yeah, so first one is possible. Yeah, true.
Yes, sir.
In your case, first one is possible. Okay. So what I'm saying is, in the first part, 3, what will be the Jordan form? If nullity of the matrix itself is 3, then the Jordan form has only one option. What is that? There will be 3 Jordan blocks. So 4 has to be split into 3 means 1 must be 2, right? So J2 of 0, J1 of 0, J1 of 0. Its Jordan form is fixed now. Now the question is, what will be the square? What will be square? J2 square will be 0 matrix, J1 square is 0 matrix, J1 square is 0 matrix. So if this is the matrix A, this is the matrix T, then T square is 0 matrix. So nullity of T square will be 0. So this part is possible. Okay. Now what about the another one? nullity of T is 1. Okay, so nullity of T is 1 means if Jordan form must be, there will be only one block. There will be only one block means it must be J4 of 0. If J4 of 0, if you get squared it, in J4 of 0 there will be 3 ones. If you square it, there will be 2 1. Okay, so if T is equal to J4 of 0, then T square will be 0 0 1 0 0 0 0 1 0 0 0 0 0 0. So this will be T square. It has nullity only 2. It cannot have nullity 3. Okay, so if nullity of the matrix is 1, then it cannot have the nullity 3 for its square. Okay, so this is not possible. Okay, now what about this one, 2 and 4, C and D. Okay, so if nullity is 2, then T have only 2 diagonals. Okay, there will be only 2 blocks. The 2 blocks can have 3 forms. I mean 2 forms: J3 of 0 and J1 of 0, J2 of 0 and J2 of 0. Okay, if you square this J3 of 0, J3 will have 2 ones. If you square it, J3 will have only 1 1, right? So this will have nullity 3 if T square have nullity 3 and here T square have nullity 4. Here if you square it, J2 square will be 0, J2 square will be 0. Here you will get, if you just square it, all the candidates will get to 0. Here if you square it, one term will remain. That's why nullity will become only 3. So these two things are also possible. So A, C and D are possible. B is not possible. Okay. So if you are not getting it quickly, you just write down the questions and think about it later. Okay. Any doubts? Okay. Some December 2015 question. A is 2 2 1 2 minus 1 and 3, and B is equal to 2 1 2 0 3. So obviously A is not in Jordan canonical form. B is in Jordan because only the diagonal elements and just above the diagonal has non-zero elements, and the thing just above the diagonals have only 1 and zeros. So B is in Jordan canonical form. A is not in Jordan canonical. The question is whether B is a Jordan canonical form of A. That is the question. So what is needed to check B is Jordan canonical form? So here A has eigenvalue 2 and 3. Okay. And if the eigenspace corresponding to 2 has dimension 2, then it will be diagonalizable and this one won't be there in the Jordan form. If it is not, then this will be. So we only need to check what is A minus 2i. So what is A minus 2i? A minus 2i is
2, sir.
what? 0 2 1 0 0 minus 1 0 0 1. Okay, so this is A minus 2i. What is the kernel of this space? What is the nullity of this matrix?
1, sir.
Yeah, so nullity is 1, means that is not diagonalizable because 2 is occurring 2 times, but the eigenspace has only dimension 1, means it is not diagonalizable in that part. Okay, then the only form is, then it must be this one. So B is the Jordan canonical form. Jordan canonical. This is some question. Okay, I will do one more problem from linear algebra and then we'll go to something else. Bottom.
Eigenvalue 2 have 1 Jordan block, so we have same answer.
Eigenblock 2 have? Yeah,
only 1 Jordan block with the 2 eigenvalue 2, so we say the matrix A is the Jordan form of B.
No, B is the Jordan form of A. Yeah. Since 2 is occurring only 2 times. So if A is like this, then if A is, the only 2 cases will occur. A is diagonalizable, A is not diagonalizable, right? So if A is diagonalizable, then the Jordan form will be 2, 2, 3. This is the, if A is diagonalizable, this is the answer. When it will become diagonalizable, if the eigenspace of 2 has enough eigenvectors, then it will be diagonalizable. Because 3 we don't need to care, 3 is only acting one time. So 3 obviously it becomes diagonalizable. So we need to care only about the eigenvalue 2. So 2 is occurring 2 times. So if it has 2 eigenvectors, it will be diagonalizable. So we need to check that. So here we are calculating A minus 2i, but in each null space there will be only one element, because the nullity of this is only 1, because it has rank 2. 2 non-zero columns are there. It has rank 2 means nullity is 1. So there is only one eigenvector corresponding to 2. Then it should not be diagonalizable. Okay. Then since it is the Jordan block of 2 will be only 2 by 2, we don't need to check other things. If it is 3 by 3, we need to check more. Here there is no other options, right? So this must be the Jordan canonical form. Understood?
Yes, sir, understood.
Okay. Yeah, then one more question from this section. Characteristic polynomial x cube into x minus 5 whole square. Minimal polynomial x square into x minus 5. So, question is 4 options. JCF can be uniquely determined. It is determined. Okay. B, 2 Jordan blocks. C, A is nilpotent on V quotient kernel of A minus 5i. D, A is scalar multiple of I equal to kernel A. Okay, so this is one somewhat interesting question came from Jordan canonical form. So you have characteristic polynomial 3 and minimal polynomial 2. So characteristic polynomial 3, I'm saying this one. Algebraic multiplicity 3 and geometric multiplicity is not given. Minimal polynomial is x square. So minimal polynomial is x square means there will be one Jordan block of order 2. And then there is only one more element left, right? So since the part of eigenvalue 0 is only 3 by 3, if you have, it should be J2 of 0 should be there and J1 of 0. There are no other options, right? If you have x cube is given, so there is only 3 by 3 matrix should come corresponding to 0. And one Jordan block must be of length 2, by order 2. It is given from minimal polynomial. So J2 of 0 and J1 of 0 is there. And what about the rest of the part? X minus 5 whole square is the characteristic part and minimal part is x minus 5. So that part is diagonalizable. So it will be J1 of 5 and J1 of 5. Is there any other option for characteristic Jordan form, or this is fine, right? So your A is true. Is it okay? Everybody?
J1
Yes, sir.
J1 of? Yeah. So Jordan canonical form is uniquely determined now. So option A is correct. What about option B? They are asking 2 Jordan blocks, but we have 4 Jordan blocks. So that's what we are saying. You should not be confused about Jordan segments and Jordan blocks. Here, there are 2 Jordan segments corresponding to 0 and corresponding to 5, but there are 4 Jordan blocks. Okay. So we can say nullity is 4 here. Nullity of the vector is 4. Geometric multiplicity of 2 will be 2. geometric multiplicity of 5 will be 2, like that. So a lot of results you will get from here. Canonical form. Okay. Now, what is the third part? A is nilpotent in kernel of A minus 5i. So, in kernel of A minus 5i means we are removing the part 5. Okay. Then, what else is there? Think about and tell me. Just think about that portion. Yeah. So if you remove that part kernel of A minus 5i, the rest of the part is just A, right? There is no A minus something. So you can write the whole space. It will be like what is the matrix coming here?
0, 1, 0, 0, 0.
0, 1, 0, 1, 0, and 5, 5. Okay. Now we are removing the part with eigenvector 5 means we don't need this part. Okay. Then what is here? It is nilpotent matrix, right?
Yes, sir.
Yeah. So that's what we are saying. So A is nilpotent on the part kernel of A minus 5i. Because kernel of A minus 5i is the whole part. If you get, this is the kernel of A minus 5i. Okay. So this is true. What about this one? Kernel of A. So what is kernel of A? Here, this whole block is not just coming from kernel of A. Here what we are doing, kernel of A minus 5i means kernel of A minus 5i will have enough eigenvectors to accomplish the whole part. So in the whole space we are dividing into two parts. The elements corresponding to the eigenvector 5 and elements corresponding to the eigenvector 0. So all the elements corresponding to the eigenvector 5 are just coming from eigenspace because its eigenvectors comprise the whole space. Okay. But what about the other part? Kernel of A means the eigenvector corresponding to 0. The part corresponding to 0. It is not coming from the whole eigenvectors, right? Because if that part was diagonalizable, then the whole part will come from the kernel. Here, this whole part won't come from the kernel because this only one eigenvector, only two eigenvectors are there. One element is not an eigenvector. So if you just take kernel A, you can only remove these two elements. This will be still there. Okay, kernel A, only these two elements are in the kernel. This element is in the kernel of A square. Okay, so this part won't be removed if you quotient out with just kernel A, because in the kernel A only these two elements. Now, then 5 and 5, and there is one more thing here. So it cannot be a scalar multiple of I on V restricted to kernel A. It will be on if it is V restricted to kernel of A square, then we are removing the whole part and we are only dealing with this part. It will be 5 by 5 and identity 5 times I. Okay, but if you are just dealing with the kernel of A, then this whole part won't be removed. Only two elements will be removed because kernel of A don't have enough eigenvectors. Okay, to comprise whole the part of the elements related to the eigenvector 0, you have to do kernel of A square. Then only that part will be taken as a whole. Okay, so D is not true. But A is a scalar multiple of I on the quotient space V restricted to kernel of A square. Understood this part? You have to think about this more. This is a question in June 2013. Okay, so the solutions are A and C. Most important part is D is not true. That is very important. Okay. Now in this time,
Sir, how is taking quotient same as removing some part? Like how can we see taking quotient as removing some vectors?
It's not removing actually. We are quotienting means if you are V with respect, we are quotienting X means Now we are dealing with the images like u plus x, right? Now the elements in that space will be u of the form u plus x. Understood? Who is that one?
Yes, sir. Yes, sir. Okay, yeah, I understood.
Till don't switch off the mic till this part is over, okay?
Okay.
So if you have a quotient space, if you are quotienting with respect to x, we quotienting with respect to x, right?
Yeah.
Then the elements of that will be u plus x.
Okay.
And x is treating as 0 here. Here that 0 element is x.
Okay.
So now we are doing the linear transformation, the entirely opposite part. So the whole x we are treating as 0. So if you have a basis u, v, w, okay, and if these things corresponding to x, and if you are dealing with v with x means, now the only basis element will be w plus x, right?
Okay.
That is, we are removing that part. I mean, now we not removing actually. We can think like that, or we can think it as a single space w. It is a one-dimensional space. It will be. You don't need to worry about that. That whole part we are treating as 0 now.
Okay, sir.
Okay. So here, if you are dealing with the things you have is kernel of a minus phi y is there, and kernel of a is there. Since kernel of a minus phi y has 2 dimension, so there will be basis, right? U and v. Sorry, u and v. These things will come from kernel of a minus phi y because it has enough eigenvectors. And kernel of a don't have enough eigenvectors. It have only 2 eigenvectors. So there will be one eigenvector, generalized eigenvector AW, W, and there will be things will be like this.
Okay.
Right? So if you quotient it out, if you quotient out this part, this will be rest of the images. The rest of the bases, only these things will comprise the rest of the bases, and here the matrix will be nilpotent.
Okay, sir.
Now, if you now this is a generalized eigenspace for the. Now, if you are just doing it with in the kernel of it, there are only 2 elements, A and Z. W is not in the kernel. So in the basis, there will be U, V, and W will be there. In that basis, it is not 5 times identity. Only in this basis, it is 5 times identity. So if you are quotienting with kernel of A square, then these all the 3 terms will come out because kernel of A square is comprised of these 3 vectors. AW is the, W is the, Z is the. So those 3 terms will comprise with A square. If you are quotienting with the kernel of A square, then only U and V are there in the other part. Then in that part it will be a 5 times identity matrix. But if it is you are just doing kernel of A, you won't get it. Got it right?
Yes, sir. Okay, I got it.
Yeah. Okay. Thank you. So now I want just to say one more important part. That is, so these are the basic things of Jordan canonical form asking in linear algebra part. So one more important part is there in system of ODE. System of ODE. So we usually, most of the people who are doing this analysis and linear algebra don't care about the part of differential equation, but please do check the differential equation part because every year, at least in December or June, they are asking one question in CSIR, and GATE it is asking regularly, I think. In CSIR net also they are asking one question on system of differential equations, system of linear differential equations. Then the important part is, if you know a little bit of matrix theory, it is very easy to do. There is nothing related to differential equations there. It is whole linear algebra in that part. Okay, so don't leave that part because I will show you one question. In June 2012, they are asking this question like x dot is equal to ax, x at 0 is equal to 2 minus 1, and where a is a vector 1 to 0 minus 1. there will be some computations here. So they are asking where this, there are 4 options like x1 of t going to what and x2 of t going to what as t tends to infinity. So they are asking questions like this. So even if it is a differentiation question, it is asking some pure analysis question. But the only knowledge you need here is linear algebra, some Jordan canonical form or something. So here the main thing is, here there is nothing to do here. It is diagonalizable because there are 2 eigenvalues, 1 and -1. Since there are 2 eigenvalues, there must be 2 eigenvectors. So the basis, it has enough bases containing eigenvectors. So it can be diagonalizable. So there is nothing to do with Jordan canonical form. But I will just say how to solve this, and then we will go to Jordan canonical form part. So here, if x dot equal to ax, the theorem of differential equation says that x is equal to exponential of at acting on x0. Okay, x is equal to exponential of at times x at 0. And what is exponential of at means? E power a is equal to I plus a square by 2 factorial plus etc. So this is what we call exponential of a. The convergence and everything you can deal it later. Now take it to be granted that it is convergent in some usual norm or something. Okay, much worried about this thing. Okay, so x is equal to e power at times x at 0. Exponential of a is equal to this one. Now here, if here the since a is diagonalizable, a can be written as some p times what will be the eigenmatrix with eigenvalues 1, 0, -1 times p inverse. You will get elements like this. Okay, then what will be e power a? E power a will be e power p 1, 0, 0, -1 times p inverse. Okay, so you can verify these things. I'm just writing it directly. This will be p e power 1, 0, 0, -1 times p inverse, because each term will be like that. Here it will be p j p inverse, p square j p inverse will be there, then it will come out like that. So these things you can verify. And this is important part. If you have an a and if it is in diagonalizable form, you can directly write this, and this is nothing but p e power 1, 0, 0 e power -1 times p inverse. So these are all the theories which are developing in ODE. You don't need this much theories, you just need these results to do the problems. Okay, so here it must be e power at. So then it will be p e power 1, 0, 0, -1 times t times p inverse. So this is nothing but p, this t will come inside. So 2 e power t 0, 0 e power -t. Okay, so p and p inverse. So what will be our x of t? X of t will be p e power t 0, 0 e power -t times p inverse acting on what is x at 0? 2 -1. Okay, so you don't need this much things. You can directly write. Okay, I have written these things just to give the intuitions. Okay, so x of t is equal to p e power t, this thing. So now to compute, so the main issue with the differential equation questions part is you have to compute a lot. Okay, so main issue is here we have to compute p and p inverse. There, I don't know is there any other easy methods other than linear algebra to do that. So anyway, I'm just trying to do this part also. So we have to compute this p and p inverse. So I hope everybody know how to calculate eigenvectors, because eigenvectors, eigenvalues here are 1 and -1. So here you will get a is equal to 1, 2, 0, -1. This is our vector. So to compute the eigenvector corresponding to a, you just calculate a minus I. A minus I is 0, 2, 0, minus 2. So this is a vector. So the eigenvector corresponding to this one must be eigenvector. Eigenvector is 1, 0. And we have to calculate the eigenvector corresponding to minus 1. It is a plus I. A plus I will be, what will be a plus I? 2, 2, 0, 0.
2,
Yeah, then the
0,
eigenvector corresponding to
0.
this, tell me. Eigenvector 1 and minus
1
1.
and minus 1.
Okay. So then what is P? P is the coordinates of eigenvectors. That is the important part here. What will be the coordinates of eigenvector? Yeah, 1, 0 and 1 minus 1. Okay. And then you have to evaluate P inverse. This is P. I hope everybody know how to compute P inverse. You can directly get P inverse also as 1, 1, 0, minus 1. Okay. Then x of t will be 1, 1, 0, minus 1 times e power t 0, 0, e power minus t 1, 1, 0, minus 1 acting on 2 minus 1. Okay. Just multiply these things and you are getting this will be equal to e power t plus e power minus t and minus e power minus t. That is x1 of t is equal to e power t plus e power minus t. So as t tends to infinity, this part will go to 0 and this part will go to infinity. Okay. And x2 of t is equal to minus e power minus t. This will go to infinity and this will go to 0.
0.
Okay. So here we are not at all using any linear differential equation concept. So here we only need linear algebra part. So here we are using the fact that the matrix is diagonalizable. Okay. So if the matrix is not diagonalizable, what will we do? That is an important question. So I am doing one problem with that. This is one question asked in June 11. Okay. Question is this one. X dot is equal to ax. X at 0 is equal to some given. It's AB. Okay. Where A is a matrix 3, 2, minus 2, minus 1. Okay. So this is a matrix. So what we can do? That is the question. So if it is diagonalizable, write it in diagonalizable form. If it is not diagonalizable, write it in the Jordan form. Okay, that's a starting. So how to check what are the characteristic polynomial will be? What will be the characteristic polynomial? X minus 3 into
X square minus
x plus 1 plus 4. This is equal to x minus 1 whole square. Okay. So there are two eigenvalues. Both are 1 with multiplicity 2. Then what will be a minus I? A minus I is equal to 2, 2, minus 2, minus 2. So what is the dimension of its kernel? Why nobody?
1, sir.
Dimension of the kernel is 1. So there are no enough, there is not enough eigenvectors corresponding to the eigenvalue 2. Okay. So we can get one eigenvalue. That is 4 easy, right? What is one eigenvalue? For eigenvector?
1 and minus 1.
1 minus 1. Okay. So now the question is we have one eigenvector. But to write P inverse, we need one eigenvector and one generalized eigenvector, right? So what will we do to get a generalized eigenvector? So generalized eigenvector means we know that A minus I is non-zero. So you will get an element such that A minus I of that is non-zero. That is enough. Okay. So you just take an element such that A minus I is non-zero. We know that it is 0 only for the vectors of the form 1 minus 1. So take 1, 0. Okay. Sorry, 1, 0 in you have to write in other form. You have to take 1, 0. What is?
Can you repeat once again, sir?
Yeah. So here A minus I has nullity 1. So you will get only one eigenvector, right?
Yes, sir.
So only one eigenvector means it is not diagonalizable. Not diagonalizable means now you can have to find a Jordan canonical form. So how to find a basis for Jordan canonical form? Do you remember? We know that A minus I is not equal to 0. If it is equal to 0, this matrix must be 0, right? So this is non-zero means A minus I is not equal to 0. So how to find out the basis for Jordan canonical form? You will get an element A minus I times U is non-zero, and then that U. This was the basics, right? You remember?
Yes, sir.
So this was eigenvector and this is a generalized eigenvector. So this is how we are creating the basis. So here also we need to find the U such that A minus I times U is non-zero. So you just need to take U which is other than an eigenvector. That is enough. Because only the eigenvectors it is problem, right? You take an element which is not an eigenvector here. So eigenvectors are of the form in the span of 1 minus 1. Take any element other than this. For example, I am taking 1, 0. You can take 2, 0, you can take 1, 1, you can take 3, 5, you can take 5, 6. Any element you can take. Okay? Because the only criteria we need is A minus I times U must be non-zero. Then only we will get a basis for generalized basis with generalized eigenvectors. So to get a generalized eigenvector, take a U such that A minus I times U is non-zero. And we know that A minus I times U is 0 only if it is in the span of 1 minus 1, right?
Yes, sir.
Yeah, so take any element which is outside this 1 minus 1. So for the most simplest vector is 1, 0, right?
Yes, sir.
Yeah. Now what is A minus I times 1, 0? It will be 2, 2 minus 2 minus 2 times 1, 0. It is 2 minus 2. Okay?
Okay, sir.
Now what will be P? P is 2 minus 2 and 1, 0. Okay? What is P inverse? I already calculated. It is 0, 2 minus 1, 2. This is P inverse. So this is how we have to calculate P and P inverse. Okay? Now you can write A is equal to Pj P inverse. That is P times what will be J, the Jordan canonical form of this matrix. The eigenvalues are only 1. So it will be, what will be the Jordan canonical form here? 1. And this is the Jordan canonical form. Eigenvalues on the diagonal and 1 on the super diagonal. Okay? And P inverse. Okay, I am writing Pj P inverse. Now we have to compute e power A. How to compute? Then it will be P inverse e power J. Sorry, P inverse. P e power J.
1, 1.
What? Yeah.
Sir, replacing with J, sir. Jordan canonical form.
Yeah. Okay. So P e power J P inverse. Okay. Now what is this one? P e power 1101 times P inverse. Then what will we do? What is this one? What is the importance of Jordan canonical form here? Here, all the Jordan canonical form, this we can write as e power 1001, right? Sorry. This one we can write as identity plus 0100, right? Is this true?
Yes, sir.
This
True,
you can
sir.
e raised to I into e raised to 0100. There is something to prove this part, but you can use this. E power A plus b is equal to e power a into e power b. Okay. Now, this is an nilpotent matrix, right? Then this will
Yes,
be
sir.
power I into, what is the definition of e power a? I plus 0, 1, 0, 0 plus a square by 2 factorial. But this matrix a square will be 0.
Sir.
Yeah, so this much is enough. Okay. Now you just come back. So this is our, so we are done. E power I, it is EE, then I plus that one. Okay. Now what will be our x of t is equal to x of t is e power at times x naught. It is p inverse e power jt times, sorry, p inverse times x naught. It is p, what is e power jt? It will be e power I into, sorry, e power it into I plus 0, 1, 0, 0 times t plus square will become 0. This much is enough. Times p inverse x naught will be p. This will be e power t into, what will be this term? This t will be the 1t01 times p inverse times x naught, or e power t into p1t01 times p inverse.
Sir, t e power t, sir.
Huh?
Sir, second term I plus 0, 1,
Yeah.
0, 0.
T e power t. Which one? Now it is fine, right? No.
Second term, sir.
E power t is enough. 1 minute. Which second term? I didn't get what, which term here. This term you are telling?
Sir,
Huh?
in third step, sir. In sir, fourth step, sir.
This one, second last.
Last but one, sir. Step. Yes, sir.
P e power.
Second term of the matrix t e power t, sir.
It is e power it is coming, right?
Yes, sir.
So what will be e power it? That is e power t0 0t, right? It will be e power t 0 0 e power t.
স্যার ই পাওয়ার টি 1 1 ই পাওয়ার টি হবে না?
Huh?
ই পাওয়ার টি 1 1 ই পাওয়ার টি.
Which term you are saying? I mean, in fourth term, in this step.
Yes sir, e to the power 0 equals to 1.
Yeah. So, no, so you are saying this one, right? E power it. What is e power it? E power t0 0t, right?
Yes.
Yeah, this will be e power t 0 0 e power t. What is the issue here? Yeah, that you can just verify. If it is e power lambda 1 0 0 lambda 2 times t, this will be e power lambda 1 t 0 0 lambda 2 t. This will be e power lambda 1 t 0 0 e power lambda 2 t. You can just give exponentials of the diagonals.
Okay sir, ঠিক আছে.
Understood?
Yes sir.
Indu, what is the issue solved now? Yeah. So now I am not calculating the p and p inverse. Here also you can just calculate eigenvector, eigenvalue and multiply, you will get the final answer. Okay. Now, for 3 by 3 questions, it is very difficult to find out this part. But for most of the 3 by 3 matrices, they are giving directly the Jordan canonical form. You have June 16, there is a question. X dot is equal to AX with X at 0 is equal to X naught and A is equal to minus 2, 1, minus 2, 1, minus 2. So what is the importance here? A itself is in the Jordan canonical form. You don't need to worry about the P inverse, calculating eigenvectors, eigenvalues, anything. Because if it is given in the general form, it will take around half an hour to compute just eigenvectors. Okay, so here the answer will be x of t will be e power at times x naught. Okay, so here what will you do? E power, what will you get? Minus 2i times and another vector. I am naming it as nilpotent n times x naught. Okay, so what will be e power minus 2 or times t? Okay, so this will be e power minus 2t times what is exponential? Okay, I will write one more step.
I plus.
So this will be into e power n t times x naught. So this will be e power minus 2t into I plus nt plus n square t square by 2 factorial plus n cube t cube by 3 factorial plus etc. times x naught, right?
Sir, 0, sir.
Yeah, here this is 3 by 3 nilpotent matrix. That n is 3 by 3 nilpotent matrix. So n cube will go to 0. So only this much we need to find out. Okay, so n square 2c square by 2 factorial, this much only. So this will be e power minus 2t times, what is the matrix here? In one part it will be 1, 1, 1. Nt, here will be t, and n square and t square will be t square. So if you just compute these things, you will get like this times x naught.
T square by factorial 2.
Sir, t square by 2.
Okay, sorry. T square by 2. Okay. So, and the question is, where will the limit t tends to infinity mod x of t will go? Okay. So, where it will go? There was 4 options. It will go to 1, 2, 3, infinity, something like that. 0. Yeah, because e power minus 2t is coming. The rest of the whole thing, all the things are some function, some random things, right? Some polynomial things only. So this will go to 0. Okay, so if they are giving it in 3 by 3 matrices, they are giving it using itself is Jordan canonical form. So you can directly write it as diagonal matrix plus nilpotent matrix. So that is the main idea of Jordan canonical form. So if a matrix is in Jordan canonical form, means you can write it as a sum of a diagonal matrix and a nilpotent matrix. So I will stop with one more problem. Very simple problem only. It was asked in December 13. X dot is equal to AX. X at 0 is equal to 1, 1, 1. Where A is equal to 0, 1, 0, 0, 0, 1, 0, 0, 0. Okay. So what will be the answer? X of t is equal to e power at times x at 0. It will be, what is e power at? I plus a square by 2 factorial, right?
Yes, sir.
So a cube will be 0 here because this is 3 by 3 matrix. So a square will be 0 here. So e power at will be I plus at plus a t square by 2. So I plus at plus a square t square by 2 times x at 0. It will be, what will be the matrix? 1t t square, 1t, sorry, 1. It will be 1 acting on 1, 1, 1. So x1 of t will be 1 plus, sorry, by 2 will be the t plus t square by 2.
1 plus t.
x2 of t is equal to 1 plus t. x3 of t is equal to 1. Okay. So that's what I'm saying. Generally, we don't, if we are working on linear algebra analysis and abstract algebra, we won't care about the differential equations part. So if you are just familiar with Jordan canonical form, you can do problems from that part also. Just every year they are asking one question on system of differential equations. I hope I completed all the things I was prepared for. Any doubts?
Okay. Good afternoon, all. I'm Adra Santosh from Government Victoria College. Sir, today's class was really helpful and it was very helpful for. Hello.
Yeah,
Am I audible, sir?
Yeah, no, yeah, I'm asking. You're from Palakkad Victoria College.
Hello, sir.
Hello?
Yeah.
Yes, sir. I'm from Government Victoria College, Palakkad. Yes, sir. Hello.
Okay, fine.
Sir, I'm audible.
Yes, Adra, you continue.
Okay, sir. Yeah, I'm Adra Santosh from Government Victoria College. Sir, today's section was really helpful and it was okay. Okay, sir. Sir, I have a doubt. Not about today's section. My doubt is about how to get admission in IISc. And how many ways can we get admission there? Can you? Okay, sir. Sir.
Yeah, Renjith, Adra is asking about being a BSc student.
Yes, sir. How to get? Yes, sir. I'm asking.
Yeah, sure. Mainly, there are 4 ways to get it. Huh? Oh, you are BSc student.
Yeah. Asking
Okay,
about PG
sorry, I
admissions.
thought about PhD. Yeah, for
integrated
degree, the main, I think there is only one way for getting masters here. It is through JAM. You have to clear. There is integrated PhD. So the only way to get here is, I think, it is through JAM. You have to get JAM. I think if it is below 100, you will call for interview. Then they will select around 5 to 6 people. So main ingredient is JAM only. And about the PhD program, what I'm saying is you can't get master in 2 years. If you want to go out with masters, you have to stay for 3 years. And there are a lot of students who are going like that. They will just do 2 years for 3 years masters and get PhD somewhere outside, like Washington University or some other universities outside. So that is a major thing in IISc. You can't, if you just want to do an MSc, you can't do it in 2 years. They won't give in 2 years. You have to stay for 3 years. And if your main aim is to do PhD, then this is one of the best option also, because in 1.5 years, most of your coursework will be over, and you can start discussing with a professor in your 4th sem. You can start doing some project and you can start discussing. And after 6 months of your PhD first year, you can complete your comprehensive and you can start get into your research fully. So after comprehensive, you are getting 4.5 years if you are joining as an integrated PhD. While you are joining as a PhD student, you will get only 3.5 years. Only 3 years after comprehensive exam. So for integrated PhD, there are a lot of benefits. So try to get into IISc as early as possible. Like what I'm saying is, try to get into IISc for integrated PhD than to get into PhD. So try to get into IISc as early as possible. Not even to IISc. I'm saying the institute, it will be better. If you are going as integrated PhD program, it will be easy to pursue. Otherwise, you have to do again coursework, and the time will be very less. Now I am facing the similar kind of problems. That's what I'm saying. If you are for integrated PhD students, and you will get much more exposure and everything. And integrated PhD is the best program offering by Maths department in IISc, I think. The only window is JAM. But for PhD, there are a lot of other windows also. And the thing is, if you get rank around in 100, you will get a chance to come for interview.
Okay. So there will be an interview also. So,
okay, sir. Thanks, sir.
Yeah, interview is the major part. Yeah, I told, right, they will select around 5. I mean, at most 10.
Yeah.
If they will be less than 10, around 5 people will be selected, but they will call. No, the issue is if you are applying for PhD, you have to get CSIR rank less than 20. Then only they will call for interview. And for NBHM, they will give only NBHM for some 35 to 40 people. So the rank cutoff, the gate rank cutoff is around 15. You have to come below rank 15, and Inspire also it is very difficult. So rank cutoff is very difficult for CSIR and everything. But if it is JAM, I think they are calling around, because since the result is only way to enter, they are making the cutoff around 100. But from that, they are selecting only 4 to 5 people for PhD.
Yeah. Yeah, IISc is the most prestigious institute in India. So getting there, of course, it will be a little bit difficult, but and at the same time, it is very promising also. Okay.
Yeah, for PhD, if you can survive here, I mean, it's not that much difficult to survive. The most difficult thing to survive is for UG. Undergrads, it is very difficult to survive here, but in PhD, you can survive if you just do proper hard work. You can survive. No difficulty at all.
Okay. Okay, others.
Hi, sir. I'm Dina K from Government Victoria College, Palakkad. Sir, today's session was really helpful. I really like the way you presented the topic, but there was a little net issue in between the class, but still it was really understandable, sir. Thank you.
Okay. So a lot of people from Victoria College. I'm also from Palakkad, NSS College.
Okay, thank
Hello,
you.
sir.
Yeah, yes. Yes, Selena, continue. No problem. Yeah,
Hello.
yes.
I'm Gayatri. I have studied in Miranda House College, Delhi. It was a nice class, but there were some network issues during the class, so it will be nice if you send the notes. Thank you, sir.
Notes. I will send you the problems, and I have, because the notes I have writing is just scribbling, right?
Yeah.
I will write down. I will write down the problems I have discussed here neatly and then I will send.
Okay, sir. Thank you.
Okay.
Thank you, Gayatri.
Hello, sir.
Yeah.
Myself, Alina Anna Matthews, third year student in Mathoma College, Tungatra. I'd like to thank sir for taking time from your busy schedule to take such a detailed and helpful class for us. I'd also like to thank Vinod sir for conducting such a class for us. Thank you, sir.
Thank you, Alina.
Hi, sir.
Yes. Yes, Harita. Yes.
Okay. Hi, sir. I'm Harita from Mathoma College, Tungatra. I'm final year student. It was a very nice session. Thank you so much for spending your valuable time with us.
All are degree students. Most of the students were degree students in this class.
Yes, we are final year students.
Yeah,
degree.
Of course, PG students are also there. See,
okay.
Those students interacted in between are all PG students.
Okay.
Thank you, sir, for this session. It was very useful and understandable. And thank you, Vinod, sir, for such a wonderful opportunity.
Thank you, Harita. Yeah, this.
Hello, sir.
Yes.
I am Vishwas from NIT Trichy. I am a MSc second year student. Sir, today's session was very nice and it was very helpful also. Sir, I wanted to ask you about the interview that you faced during your PhD admission. Can you share your experience and interview of IISc?
Yeah, my interview experience was, I mean, the easiest interview I faced was IISc interview. I mean, for everybody, it will be like that. Those who got selected somewhere, that will be their easiest interview. I think they asked mainly from very basic subjects only. In big institutes, they will do like that only. If they won't ask from very big subjects, they will give ask from very basic questions from real analysis, very basic stuff. For me, one example I will tell you, like, I will tell you one important part. They asked one question from complex analysis, like some real part is not there or something. complex function, entire function whose real part is, sorry, in the range the real line is not there. A positive real line is not there. Okay, so then I answered like it is trivial from Little Picard's theorem. Because we have, while learning for net, we will learn like for Little Picard's theorem, an entire function's range can omit at most one point. So I said like if the entire positive real line is not there in the range, it means that it is not there in the, it must be constant. Then they asked like whether you study Little Picard's theorem in your master's course. Then I told that I didn't study it. Okay, then do it with something you have studied, because you can do it with Liouville's theorem, and I was using Little Picard. Little Picard theorem is very, very big result. It will be like something if they want to calculate 1 + 1 the whole square and you are using the expansion of a + b whole square. It will be like that. So that question you can use Liouville's theorem and do it, but I was trying to do it with that part, but then they gave some hints and then I could able to do that. Okay, then they just start from the beginning, like if mod f is less than 1, you can use Liouville's theorem. What can you do with if mod f greater than 1? Then you can use 1 by f, and again it will be entire with that part. Then you will get it is constant. Then using the same result, if you just take any unit ball, then you will get it is something dense. Then they proved that then it must be dense, range must be dense. They reach something like that. Then they gave some hint for taking square root function, something like that. So with this process, I reached the answer. It is not like I directly found the answer. They will give hints. So in most of the institute, it will be like that. They will give hints and we have to reach the answer. So one difficult part of preparing for net exams is we are trying to get shortcuts all the time. Like whenever we want to solve something very simple, we will go to direct very big results and we are proving it. Like this one. In all the net exams, they are asking these kind of questions. Real part, positive real axis is not the real part is bounded, imaginary part is bounded. These kind of things they are asking all the time. And we are all the time we are solving it using Little Picard's theorem. But it can be solved using Liouville's theorem, but in interviews, if they are asking this kind of question, we can't use this much big results. Like the similar thing in some problems in differential in linear algebra, if it is direct question, we will use Jordan canonical form. So that is also a difficult part. If they are asking questions and if for a simple part, if we are using Jordan canonical form, that is also difficult. Okay? So be cautious if we are using tricks in net exam. If you are using lot of tricks in net exam, it will get difficult for your interview, because those kind of tricks you can't say in an interview panel. You have to do it with proper results. That's the issue.
Okay, sir. Thank you, sir.
Yeah, thank you, Titi. I think Subra Kundu started to speak some.
Yes, sir. Yes, sir.
Yeah.
Sir, thank you, sir. Very nice session, and solving of system of ODE through Jordan canonical form. It is very new angle near me.
Yeah.
Oh, okay.
Subra, you can.
Thank you, sir.
Subra, you can introduce yourself.
Yes, sir. I am Subra Kundu and I am coming from WB, West Bengal. And I complete PG course completely. And I'm preparing the NET exam.
Okay.
Yes, sir.
Okay, thank you, Subra. Yes, yeah,
in differential equation part also there will be some questions that will be doable.
Good afternoon, sir.
Yeah.
Yes, sir. It is very new angle. System of ODE.
അത് മാറി അതിങ്ങനെ ഒരു വീക്ക് അപ്പൻഡിക്സിൽ ഒരു വീക്കം മാത്രമേ ഉണ്ടായിരുന്നുള്ളൂ. അങ്ങനെ വന്നത് മറ്റേ സാധാരണ തന്നെ ഓരോ ഇത് അടിഞ്ഞു കൂടിയിട്ട് അങ്ങനെയൊന്നുമില്ല. അപ്പൊ മരുന്ന് കഴിച്ചിട്ട് തന്നെ രണ്ടാഴ്ച മാറി. ഞാന് ഇവിടെ ഒരു മുരളീകൃഷ്ണൻ എന്ന് പറഞ്ഞ ഡോക്ടർ
Mridula, please unmute. Sorry, please
Sorry,
mute.
sir.
Okay, okay, no problem. Yes, any others?
Yes, good afternoon, sir. Session
Yeah.
was very nice, but I joined last part when you are solving problems, and I was listening on bike. I was on pathology, so I not listen whole session. Sir, can you please suggest some resources, reference book, textbook?
Okay. Dharmendra, you please introduce yourself.
Any textbook
Dharmendra Singh from
with
BARC
Vinod.
Vizag Library as library technician.
Yeah, Renjith, Dharmendra is asking about some reference books for preparing this canonical Jordan forms. Renjith?
Yes, any books on algebra will have Jordan canonical forms, but I suggest name one by Carl D. Meyer. CARLDMA. Sir?
Yeah, you can type it in the chat box if possible. You can type the name of the book in the chat
You're
box
telling
if
something?
possible.
Sir?
Yeah, yes, Renjith?
Hello?
Yes.
Oh,
Some net issues is there, I think.
1 minute, try the chat box.
Ranjit, you can include some reference.
Yeah, I was searching for
Yeah,
the.
Ranjit, you can include some references in the notes that you are sharing. Okay.
Very good.
Okay.
Yeah, 1 minute, I am typing.
Yeah. So, any others? Anything to comment?
Okay.
Yeah. Anamika? Yeah, Ranjit is see the chat box. Book suggestions were there. So, any others?
Sir, am I audible? Sir?
Yes.
Sir, I am Anamika from ᴊᴏʀᴅᴇᴛ College, Kozhikode. So thank you for this session. It was very nice, and there is a little bit confusing things because I'm from BSc Maths third year, but it's okay. I tried to understand more, and thank you for mentioning the reference books, and thank you, sir, for this nice session.
Okay.
Thank you, Anamika. Anu? Or any others? Gopika, Malavika, Nandakumar. So if there is anyone wish to make any comments, you can do it now. Otherwise, we will wind up here. I think.
Am I audible?
Yes.
Thank you, sir. Thank you, sir, for this wonderful session. It was really helpful for us. And also, thank you for spending this much time with us. Thank you, sir.
Thank you.
Thank you, Malavika. So, Renjith, once again, thank you. Thanks for being with us with Maths Aspirants since around 5 years, I think.
I was a product of Maths Aspirants, so.
It's actually the success of our entire initiative. There are many people now in many institutes started with our groups.
Yeah, maybe. I was from the beginning, right? The first.
Yeah. In 2017 itself.
Yeah, so in 2017, Pooja introduced me to the group. Pooja.
Yeah.
She was your student, right? In your course.
Yeah. Yes. Pooja from Tirur.
She added me to that group. At that time, very less number of people were there.
Yeah. In the beginning, we have only few people and only that WhatsApp platform. No other. All these things, online sessions and online tests are the product of the COVID pandemic.
Yeah.
Okay. So, Renjith, if possible, you can share the notes in PDF. Okay. No problem with that. It is in that writing format. Interested people can get the necessary things out of it. Okay.
Okay, sir. I will just write the problems and I will send it. Notes. The beginning part, it's not needed, right? The definition of Jordan block or anything.
Yeah.
Even
you can give the hints to do the problems, I think, if possible.
Yeah, okay. Problems and hints, questions and hints to the problems I will do.
Okay. That we can share with the recording of the video.
Okay.
So once again, thanks to everyone for being with us. Thank you, Renjith. Let us wind up here.